Let us talk about the external mechanical irreversibility and the processes that exhibit these things. The first one is the isothermal dissipation of work. Now, let's consider the isothermal dissipation of work through a system into the internal energy of a reservoir. So, I write it down. Let's consider the isothermal dissipation of work through through a system. So system becomes the facilitator of the dissipation of work into the work gets transformed into the internal energy of a reservoir. Internal energy of a TER, and in this case the TER are the surroundings and at a temperature T. Okay, so we will represent this with the help of this diagram, which shows the flow of an electric current I through a resistor, okay, in contact with a reservoir. Now at steady state, the internal energy of the resistor, that is R, and hence its temperature is constant. Okay, so if you invoke the first law, which is W is equal to, you can say W plus delta U is equal to Q. Okay, so because it is at steady state, the internal energy of the reservoir and the, you can say, the surrounding is at a constant temperature, so this delta U becomes 0. So the first law reduces to W is equal to Q. Now the flow of current, it represents the work transfer. So this input work is representing the work transfer into the system. Now at steady state, the work is dissipated isothermally into heat transfer to the surroundings. Okay, so let me tell you this. So you put in some amount of work, and that is possible with the help of the current flow through the resistor, and this work input, it gets dissipated in the form of heat, and that heat goes to the surroundings, which is at a steady state, okay, and a constant temperature. So this heat dissipation is at isothermal conditions, or you can say the work dissipation into the heat is at isothermal condition. Okay, now since the surroundings absorb Q units of heat at temperature T, okay, so delta S of the surroundings, this is equal to Q upon T. Now Q is equal to W upon T, so we can write W upon T. Okay, now at steady state, okay, we can say that the entropy change of the system will be 0, because nothing changes at steady state. There is no change with respect to time. So you can say that delta system is equal to 0. So if you find out or write down the value of delta S for a universe, which is equal to delta S of system plus the delta S of surroundings. Now because this is a 0 value, so this becomes equal to W upon 2. Okay, so you can say that the irreversible process in this case is accompanied by an entropy increase of the universe. So the entropy increases in this case of the universe. So and the value is W upon T. Now the next case is of adiabatic dissipation of work. Now let us say let W is the stirring work. So this is a stirrer. So it rotates and stirs up a liquid inside this chamber. Okay, there is some liquid inside this, and this liquid chamber is insulated from the outside, so there can be no heat interaction to and from the surroundings. Okay, now the work input is W to this, right, and this is insulated from the outside. Okay, now this work which is supplied to the thermally insulated liquid, okay, it is dissipated adiabatically into the internal energy increase of the liquid, because this work cannot move outside the system, so this is 0. So whatever work we input, it actually increases the internal energy of the system, that is the liquid, and that is to adiabatically. Okay, and the temperature, let us say, is Ti initially, it changes to Tf, and this change would be an increment because you are supplying some energy into the system which increases the energy of the system. Okay, now since there is no flow of heat to or from the surroundings, we can say that delta S surroundings is 0. Now let's find out the delta S for the system. Okay, now because the process that is being done is an irreversible process, so you take your state from I to F, and that is to from a or through a irreversible path. Okay, now we cannot perform the integration or the calculation of entropy change of the system via this irreversible path. We cannot do this, so we need to replace this irreversible path with the with a reversible one, and that too within the same state. So this this dark line, it represents a reversible path. So with the help of this reversible path, we can perform the integration and find out the entropy change of the system. Okay, and that too between the same states I and F. So that would be equal to, so delta S for a system is equal to, for a reversible path from I to F, and this is equal to dq upon T. Okay, so this is equal to R I to F. Now dq is equal to Cp dt. This becomes Cp dt upon T, as same as the previous video calculations. Okay, so this becomes Cp natural log Tf upon Ti. So if you now find out the delta S for the universe, okay, so this is, we know, is delta S of system plus the delta S for surroundings. Now there is no heat exchange for surroundings, so this becomes 0, and the total value of entropy change of the universe is Cp log Tf upon Ti. Now this is a positive value because the value of final temperature is greater than the initial temperature, because there is a rise in the internal energy of the system. Okay, so this also brings about an increase in the entropy of the universe by performing an irreversible process. Now this was the video in which we showed the processes which had external mechanical irreversibilities. Now after this, let's move on to the next topic and talk about entropy transfer with heat flow.